This is our last short answer question from Unit 4. Same setup, two pendulums with the same mass, the same angle. One has a longer string. This one says, Part A, consider the instant in each block's motion when the string is vertical. Is the speed of the block at this instant greater for setup A, greater for setup B, or the same in both setups? So we answered this question in the previous one. The block will be going faster in case 2 because it has a greater height drop. And so for each of the setups, mgh is equal to 1/2 mv squared, where h is the change in height, and then v is the velocity when it hits the bottom there. With the longer string, we're going to have a higher drop and therefore a higher speed. So 1 point for part A. Now part B is the paragraph, which says the acceleration is the same for both blocks when the strings are vertical. In a clear, coherent paragraph length response, do the following. First, explain your reasoning for your response to part A, and then explain why the acceleration could be the same for both blocks. You don't need to show mathematically that they're equal, just provide reasoning for why they could be equal. So here's what I wrote, and I'm going to repeat myself a little because I was explaining part A. Since the longer string results in a larger delta H, and since mg delta H equals 1/2 mv squared, where v is the speed at the bottom of the swing, a longer string results in a faster block. But the acceleration could be the same because the net force at the bottom here is the tension minus the weight. So our free body diagram here is mg, and our tension is there. Now, it's not balanced out because the net force is a centripetal force, right, which is equal to mv squared over r. And remember, the net force is always equal to ma. So the net force is, in both cases, T minus mg, which is equal to mv squared over r, which is equal to ma. I guess I didn't need to repeat myself. So in case 2, where the velocity is larger, okay, the radius is also larger. So that could create the same acceleration in both cases. Again, they don't ask you to show that, and they haven't given us any numbers to do so, but that ends up being the answer to that question. And if you remember this, it might even help you, right? We can do this here, right? This is kind of a square root relationship, so it's not possible, it's very possible. And that's the way you answer that. And I know that's sort of not usually how we answer questions, but they throw that at us every once in a while. So what are the points? 1 point for saying a longer string equals a bigger height change. 1 point for saying that increases the kinetic energy and therefore the speed. 1 for indicating that the mass is moving in a circle, which means it's a centripetal force. So maybe you don't even, it says which may indicate the expression mv squared over r. So you may not even have to use the word circle, but if you have the net force is equal to mv squared over r, you get that point. 1 point for saying a faster block means a higher velocity, and a longer string means A could be constant. All right, let me say that again. A faster block means a higher velocity, and a longer string means that acceleration could be constant. So V could increase, and R could also increase. And 1 point for a logical paragraph. So 1, 2, 3, 4, 5 points for that. Now, similar question about the mechanical energies from last time. Okay, we've got the same deal. Half of the block flies off at the bottom of the trajectory. Now we've got, for the system consisting of the 2 blocks only and not Earth. Okay, so what that's telling you is that gravity is external to this system. In which of the following time intervals, is the total mechanical energy of the system the same at the beginning and the end of the interval? Now, interval A, immediately after the blocks are released to immediately before the tape fails. So that's the top of the swing to the bottom of the swing. Gravity is external to this system, so even though you could make an argument if gravity were in the system, that mechanical energy was conserved. Gravity's outside, so these blocks actually gain mechanical energy during the first interval, so that's no good. Interval B is immediately before the tape fails to immediately after the tape fails. So I see that as happening instantly when the blocks are at their maximum velocity. So I would say that mechanical energy is conserved during that interval. The height doesn't increase at all, so gravity is not able to do any work on it, either positive or negative. But let's read interval C. We have to deal with them all anyways. It's not multiple choice. But interval B, I would say, is short enough that the height can't change, and so mechanical energy is conserved. Interval C says immediately after the tape fails to the instant the top block reaches its maximum height. Mechanical energy certainly not conserved there. The top block is losing energy. The bottom block is gaining energy, but it's not a linear relationship. And since gravity is external to the system, it's not conserved during that interval. So the answer is interval B. 1 point for that. And then you can get your justification point 2 different ways. You could either say there's during that short interval, there's no work done by any internal forces, or you could say the speed doesn't change. And that's absolutely fine, because if the system is just the blocks, we can't have any potential energy. We can only deal with kinetic energy. And since the mass or the mass of the system isn't changing, we can just take it from a speed point of view. So 2 points for part C. Part D, now we're going to actually deal with the projectile portion of this problem. We have 2 experimental setups are constructed that use strings of the same length and blocks of different masses. The strings are at the same initial angle from the vertical when each block is released, as shown above. This time, the string in each experiment breaks when it's vertical, as shown in the figure, and then each block falls to the floor, as shown at the right. So they want to ask you if the horizontal displacement from where the string breaks to where the block hits the floor is greater for the lighter block, the heavier block, or the same for both blocks, and briefly explain your reasoning. Now, hopefully, you recognize this as really a Unit 1 question from the time when we didn't really care what the mass of any object was. In all of those projectile questions, we never once discussed what the mass was, not because we were ignoring it, but because it doesn't matter. So the horizontal displacements are the same. Heavy block, light block. Okay, so here's my reasoning. Since they both fell from the same height, right? We use conservation of energy there. We know that their final speed is equal to rad 2gh, okay? So we know that each of their speeds are the same when they're launched, okay? So this is launch speed, right? And they're both horizontal, the projectiles, so theta equals 0. So then we can say their Vx's are equal, okay? So delta x is equal to Vx delta t. So we've already shown that the x's are equal, but are the times equal? Well, since they both fall from the same height, yes, and delta y equals V initial t plus 1/2 at squared. The initial y velocity is 0 because it's a horizontal projectile. Both of them are under gravity, so the times are the same. So since the times and the velocities are the same, their horizontal displacements are the same. So 2 points for part D, 1 for saying that their velocities are the same when the string breaks, 1 for saying the times are equal, and therefore the displacements are equal. And that's it for this assignment.